Narrator voiceover. Imagine a world where machines don't just process data but understand it, context, nuance, and all. This isn't science fiction. It's the reality powered by transformer architectures, the backbone of modern AI. But how do these models truly work? What makes them so revolutionary? Let's dive deep into the mechanics, the breakthroughs, and the future of this transformative technology. Section 1. The birth of transformers. Before transformers, sequence modeling relied on recurrent neural networks, RNNs, and their variants like LSTMs. These models processed data sequentially, which limited their ability to capture long-range dependencies. But in 2017, a paper from Google introduced a radical idea: self-attention mechanisms. Instead of processing text one word at a time, transformers analyze all words simultaneously, weighing their relationships through attention scores. This shift wasn't just incremental, it was a paradigm change. Transition. But how exactly does self-attention translate into computational power? Let's break it down. Section 2. The inner workings of self-attention. At the core of a transformer is the self-attention layer. Here's the math. For each word in a sequence, the model generates 3 vectors: queries, keys, and values. The attention score between 2 words is calculated by taking the dot product of their query and key vectors, scaling it by the square root of the key dimension, and applying a softmax function. This score determines how much each word focuses on others. The final output is a weighted sum of the value vectors, effectively allowing the model to contextualize each word based on the entire input. Let's visualize this. Take the sentence, "The cat saw the mouse." The word saw doesn't just relate to cat or mouse in isolation, it forms a relationship with both. The self-attention mechanism captures these interactions, creating a rich, contextual representation that RNNs could never achieve. Transition. While self-attention is powerful, it's not without challenges. Enter positional encoding, how transformers handle sequence order. Section 3. Positional encoding and the curse of order. RNNs inherently preserved sequence order through their recurrent connections, but transformers are permutation invariant. To fix this, researchers introduced positional encoding, a set of learned vectors added to word embeddings that encode each token's position. These encodings aren't static. They're derived from sine and cosine functions of different frequencies, allowing the model to extrapolate to sequences longer than seen during training. Think of it as a clockwork mechanism. Each position in the sequence has a unique timestamp embedded in its representation, ensuring the model knows what comes next without losing the global context. Transition. With self-attention and positional encoding, transformers became a game changer. But the real magic lies in their scalability. Section 4. Scaling up, from BERT to GPT. Models like BERT and GPT demonstrated the power of pre-training on massive corpora. BERT's bidirectional training allowed it to understand context from both directions, while GPT's autoregressive approach excelled in generation tasks. But the real breakthrough was the sheer scale: billions of parameters trained on terabytes of text. This isn't just more data, it's a shift in how models generalize. A transformer isn't just memorizing patterns, it's building a probabilistic understanding of language itself. Here's where it gets technical. The attention mechanism's complexity scales quadratically with sequence length. That's why innovations like sparse attention and linear transformers are critical. They reduce computational overhead without sacrificing performance. Transition. But what's next for transformers? The field is evolving rapidly. Section 5. Current research and future frontiers. Today, researchers are exploring hybrid models that combine transformers with other architectures, like convolutional networks for spatial reasoning. There's also the rise of mixture of experts, MOE models, which route parts of the input to specialized subnetworks, improving efficiency. Meanwhile, work on efficient transformers, like those using factorized attention or parameter sharing, aims to make these models viable for edge devices. Beyond language, transformers are being applied to vision, protein folding, and even quantum computing. The underlying principle remains the same: capture relationships no matter the data type. Closing. Transformers aren't just a tool, they're a new way of thinking about computation. They've redefined what's possible in AI, but the journey isn't over. As researchers push the boundaries of efficiency, scalability, and generalization, the next breakthrough could be just around the corner. For now, one thing is clear: the transformer era is just beginning. Narrator voiceover. Thanks for watching. If you want to explore the math behind attention mechanisms or dive into the latest research papers, check the description. Stay curious and keep pushing the limits of what AI can achieve.